Okay, so it's Friday, September 30th, and if you are accessing this video, it's because maybe you were gone on Friday, and so I am just recording this live for those who are here, and so that you don't get behind. We're writing homework 7 today, which is page P31, 2 through 32, the even, and it's due on Tuesday, 10/4, and we're doing notes on 07. And I'll try to write some in yellow and then get rid of that. I think this heading was up there yesterday. This is probability with permutations and combinations. To be honest, when I graded the pre-test for this chapter, this is a section where people did actually quite well. It's my guess that you're using the calculator and, finding the, permutations of 6 things, taking them 4 at a time or whatever. And so I'm not going to skip this section because I feel like some of the reason that we did well on it, which is good, is that we have access to the calculators. And then the one, I think it was about cards, I can't quite remember, that was asking you to find something about the probability of the outcome. That one didn't go as well, and that's where you actually have to find what you're doing. So we want to be able to find the number of possible outcomes of an experiment, and we use permutations and combinations with probability. Probably in your previous exposure to this type of section, you've had a lot of, hopefully you've had a lot of hands-on, more kinds of, maybe writing out all the outcomes and things like that. We want to move ourselves to being able to kind of make a decision whether we want permutations or combinations and kind of go from there. Just a little note to self, and this is just one of those little math things. Out in the hallways, your locks are called combination locks. Do you agree with that? That they're called combination locks, but really that would mean if they were a combination lock, so I'm talking about the English language versus true mathematics. They're called a combination lock, but that means if they were a combination lock, if your combination was like 2 3 4, then anybody could use 2 3 4 4 3 2, any order of those, because in combinations order is not important, and they would be able to open your locker, and that's not true. So really a locker is really a permutation lock, because order it is important. And so like 2 4 3 and 3 4 2 are two different permutations of the set of numbers. So just a little reminder about that. I think this slide was up. If those in the room would give me a head up, that would be great. So an experiment is simply a situation involving chance or probability that leads to specific outcomes. The set of all possible outcomes is the sample space. And sometimes we use the fundamental counting principle. The fundamental counting principle is something you want to know and be aware of. And, a typical problem is like a pizza problem. How many different ways can you make a pizza if you can have, 3 kinds of crusts, 8 kinds of toppings, and things like that? Or how many outfits can you make if you have 2 pairs of pants and 4 shirts and I don't know, 3 pairs of shoes, I guess, if you wanted to put that in. So if A and B are 2 events, if A has n sub 1 possible outcomes and is followed by event B that has n sub 2 possible outcomes, then in event A followed by event B has n sub 1 times n sub 2 possible outcomes. And then independent and dependent events, you probably remember that from earlier as well. An independent event is where the events with outcomes that do not affect each other are called independent events. The most simple example of that is, you roll a die once, You pick it up, you roll a die again. And so really, does the fact that you rolled it a first time have an effect really on the outcomes when you roll it the second time? No. Dependent events are events with outcomes that do affect each other. And, you know, an easy example of that is you go up to one person, you say pick a card, and they take a card, and then they keep it. Then you go up to another person and tell them to pick a card. Well, the first person, how many cards were in the deck if it was a full deck? 52 cards. And so then for the second person, how many cards were in the deck? 51. And so those would be dependent. And we can easily make that independent if that first person gives back the card, and then we kind of go from there. And I will go through like a little bit about the um, just kind of writing out everything that you can do, and kind of where this is coming from as we look at these. So this first one is the fundamental counting principle. Restaurant offers a dinner special in which the customer can select from one of 6 appetizers, a super salad, one of 12 entrees, and one of 8 desserts. How many different dinner specials are possible? Actually, it kind of makes me laugh when I read this because my mom is elderly. She lives with us, and my husband's parents are elderly, and we go out to eat, and it is just so hard for them to decide what they want. And so the more choices, you know, the more difficult. So you have 6 appetizers, super salad, so you have 2 choices there. Entrees, there are 12 choices. Desserts, there are 8. And so to figure out the total possible different dinner specials you could put together, it's 1152. And just to kind of let you know, how would you set this up if you weren't sure? So if you weren't sure, you could actually set up a nice little tree. So there are 6 appetizers, 1, 2, 3, 4, 5, and 6. And from every one of those appetizers, you can go out with 2 choices of super salad, that choice. And then, you know, then it gets a little hard to kind of map that out. That's why we want a numerical method, because from each of these things, like, you know, we'll say this person had appetizer number 1, they had soup, but then there are 12 entrees that have to come off of there. And so a little hard to kind of draw all those. And then from every one of those 12, there are 8 more desserts. So you can think about that as a tree diagram. And we want to be away from a tree diagram in this level of mathematics, but when in doubt, you know, that is kind of a go-to method as you look at that. And then Garrett works for a bookstore. He's arranging 5 bestsellers for a shelf display. If he can place the books in any order, how many different ways can Garrett arrange the books? And this one I'm going to say, you know, here's my shelf. You know, I'll pretend to put my books. My books are going to go on the shelf right here. I have 5 books, 1, 2, 3, 4, 5 books. So when I'm going to place this first book right there, how many choices of books do I have? 5. I can put any of my 5 books right there. So I have 5 choices that I can use. Well, when I choose that, then when I go to put the next book on the shelf, how many books now do I have to choose from? Now I have 4, and then I have 3, and then I have 2, and then I have 1. So 5 times 4 times 3 times 2 times 1. And you probably recognize that as a factorial. Do you remember a factorial? And you have that little exclamation point. I am going to go through the mathematics behind permutations and combinations. So I'm quite sure that you are well versed with the buttons on the calculator, but I want to make sure that mathematically you know what's happening there, so that you can manipulate things that are a little bit more involved. So that was 120 ways. And if you remember, factorials grow very rapidly, and so that was 5 factorial. This 5, 4, 3, 2, 1 is 5 factorial, and the factorial of a positive integer n is the product of positive integers less than or equal to n, and it's given by this equation. And you need to know that 0 factorial is defined as 1. So don't forget that 0 factorial is defined as 1. Then permutations are where order is important. Let's see, n objects can be arranged in a certain order, and the arrangement of n objects is called a permutation, if order is important. So the number of permutations of n objects taken n at a time is the permutations of n things taken n at a time, and that is n factorial. If you have n things, but you're taking them r at a time, and permutations, so order is important. Order is important. Then it's n factorial over n minus r factorial. Permutations of n things, taking them r at a time. Generally, when you're doing problems, the hardest part to think about is order important or is order not important? Because sometimes once you have, that under your belt, then it's just a matter of finding the permutations or combinations, whichever it is. So the next problem here is an alarm requires an 8-digit code using the digits 0 through 9. Each digit may be used only once. So just like your lockers that are called combination locks, they're really permutation locks, because is order important in this alarm system? We would expect it is, right? So order is important. So I'll just write myself a little note. Order is important. And so this is permutations, and we have the digits 0 through 9. So how many digits do we have? How many digits are 0 through 9 in 0 through 9? 10 digits, right? So that's the thing to be careful of, that there are 10 digits. 10 digits. So then our number of digits is 10 that we can use. We need a 7-digit code, so R is 7. We're going to take the permutations of n things, taking them r at a time, which is n factorial over n minus r factorial. And so permutations of 10 things, taking them 7 at a time. Now I'm gonna approach this without a calculator, and I'm gonna tell you that kind of in your head that might just go a little easier, because I'm also going to do it in a different way, and just kind of remind you the way that you maybe have done that before. So 10 factorial over, this is 10 minus 7 factorial, and so that's 10 factorial over 3 factorial. When I do that, really our mathematical way to do that is 10 times 9 times 8. Ooh, let me try that one more time. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. Generally, when you're going to cancel those things, you write down to whatever the highest factorial is that you can cancel. And I say the highest factorial that you can cancel, and there's only one factorial in the denominator, this 3 factorial, but sometimes there will be 2 factorials down there. Then we can cancel those. And the reason I want that illustration, and then when you multiply that, I don't know, it's a big number, 604,800. And I want you to compare that to the books on a shelf problem, okay? The books on a shelf problem, and I'm just going to go back to this a second, wherever it was. Was it back another slide? Okay, the books on a shelf problem where we did this, and I'm going to write on in yellow so that I can maybe get rid of that. So the books on the shelf problem, I had 5 books, so I had 5 that I could put there. Once I put that one there, then it's kind of glued down, so to speak, and then I only have 4 choices of what I can do there. So this problem that we just looked at, if you forget how to do permutations or combinations and you want to be able to do it, you can apply this same reasoning to the alarm code. So when you are going to, we'll say, set that alarm, how many, you're going to have 7 little boxes like my blue boxes there. But in that first box, how many choices of a code do you have? You have 10 choices. So I'm going to erase all this, but I think I'm going to show it on here. 1, 2, 3, 4, 5, 6, and 7, right? It's a 7-digit code, correct? 1, 2, 3, 4, 5, 6, 7. So now I have 10 choices there: 9, 8, 7, 6, 5, and 4. So if you have to kind of process that using kind of an example like this, look now at that problem that we just did. Oops, I went too far. And notice that what we end up doing when we set up this permutation problem is 10 times 9 times 8 times 7 times 6 times 5 times 4. And both of those should work out the same way. And so if I kind of thought about, and now you know what, I want to move that, but before I do, I'm gonna get rid of all this yellow, because otherwise I'll have a little, it is hard for me to, well, get rid of. I have to see if, there we go. All right. Hopefully I didn't erase anything else. So I just wanted to kind of go through that process and say, if you do struggle to kind of figure out, is it permutations, is it combinations, you know, is order important, what am I doing, you can, 1, 2, 3, 4, 5, 6, you can just kind of go, okay, well, I have 10 choices there: 9, 8, 7, 6, 5, and 4. So as kind of a fallback plan. We want to use permutations, but we want to understand what they are. So then the next thing asks that if the code is randomly generated, what is the probability that the first 3 digits are odd? So we're going to say this is the probability that the first 3 digits are odd as we look at that. Now, I just want to say that above here, this is the total number of outcomes, right? We didn't find the probability of anything yet. So we haven't found any probability, but we know our total possible outcomes. And when I do probability, I think of it always as a fraction, wins over total possible choices, right? Does that make sense? Wins over total possible choices. So when I think about doing this, I want to think about the ways to select 3 odd digits, but how many digits am I choosing altogether? 7 digits, right? So what about those 4 digits? Those remainder 4 digits, can they be anything? Yes, they can be, right? So when we do this, we have to kind of, to win, I have to have how many digits in my win? 7, right? We have to have 7 digits in the win. And how many possible total outcomes are there? I can't see it anymore. 604,800, correct? Okay, so when I do this, I'm going to think about ways to pick the 3 odd digits. Now, when I pick those 3 odd digits, how many winners are there of odd digits? 5. So when I'm picking these 3 odd digits, it's out of the 5 odd digits. Odd numbers, I'll say. Digits, numbers. Do you agree with that? Because this is my wins. So it's picking 3, but out of the 5 total odd numbers that I have. And then I'm going to multiply that by the ways to pick, the last 4 digits. Last 4 digits. And where are they coming from? Where are those last 4 digits coming from? Well, anywhere, but what? Remember, because this is a winning situation, right? So I've used 3 odd digits to win, right? So to get the rest of my win, I'm choosing these 4 digits out of how many odds and how many evens? From 2 odds and 5 evens. Do you agree that's going to be the win? Does that make sense? So I'm getting 3 odd digits out of the 5 odd digits, and I'm getting the last 4 digits out of the 2 odds and 5 evens that are left, excuse me, over the total possible, is that 2 S's? Yes, it is. Sorry. Okay, I can't get rid of that. Total possible choices. So I had that equal sign there. So then when I do that, I'm really looking at, and is it still permutations? I mean, that's all we're doing. But do you agree order is important, right? Even though any win is 3 odd digits at the beginning, every different set of 3 odd digits is a different win, right? So, so it is permutations. So to get this part of the win, I'll just kind of circle it in this purple, and then maybe I'll write it in purple. To get that part of the win, what do I have? Permutations of how many things taking them how many at a time? Permutations of, I want to win here. How many do I have to pick out of? 5. The permutations and how many of them am I picking to be winners? 3. Permutations of 5 things, picking them 3 at a time. And I'm multiplying those because it's that kind of fundamental counting principle. And then how many choices do I have for this other part? Oh, I was going to do a different color. How many choices do I have for this part of the win? That I'm picking out of. I'm picking out of 7 digits, and how many do I need? 4. So permutations of 7 things, picking 4 at a time. I almost forgot. And then that's over my total possible choices, which was what? The 604,800. And I'm going to write that as a permutation because just remember that was the permutations of 10 things, choosing them 7 at a time, even though we know what that number is. So then we'll kind of figure this out, and I'm going to write it out kind of so that I'm canceling a bunch of things. So the permutations of 5 things, choosing 3. Can I jump to that's 5 factorial over 2 factorial? Is that okay? Or do you want me to write it as 5 minus 3 factorial on the bottom? Tell me. Okay, so I'm going to rewrite this part. How do I find the permutations of 5 things, taking them 3 at a time? 5 factorial over 5 minus 3 factorial, which is 2 factorial. That's what I was going to ask. Permutations of 7 things, taking them 4 at a time. That's 7 factorial over what? 3 factorial. And then this one, I'll just write that that number because we already kind of did that. That was 604,800. right? Because do we agree that we did that part? So I just leave that denominator down there and I figure out the rest. So the way that I'm going to write this out is I'm going to write 5 factorial over 2 factorial as 5, 4, 3, 2 factorial over 2 factorial times 7, 6, 5, 4, 3 factorial over 3 factorial. And these are all multiplied. I kind of just said them. So, and then that's all over this 604, 800. And really, in my world, it kind of should feel good to actually, you know, kind of see what's happening there and kind of reflect back to that writing things in the boxes. Or do you see where that writing things in the boxes comes into play here as well? So I had 5 odds, then I have 4 odds, then I have 3 odds left. And then the tricky part here is that it's 7 there. Does everybody understand why it's 7 there? The reason it's 7 there is I just won with my 5, 4, and then 3 odds. So I still have 2 odds left and all the evens. So I get 7 choices for that position, then 6, then 5, then 4. And I must have what that is. So that is 50400 over 604,800. Will you take your calculator right now, divide that, and then go math, enter, enter, and see if it gives you the fraction? Well, I think it should. Okay, yeah. And I just want to go over that because a lot of times when we have these big fractions, we want to be able to make it so that they can, you know, be reduced. What is it? Did your calculator give you 1/12 then? Okay. And so I just want to kind of say that the calculator will do that. And I know that you want to use the calculator, and I'm not going to tell you you can't do that, but I'm going to tell you that, you know, to kind of get that little firmer in your head, that might be a good idea. All right, so that is the permutations part, and then combinations we'll save until Monday, if that's all right with you. Okay.